Welcome to Fein Zone, the best zone to learn about modern physics and the secrets of the universe. Today, we dive into a phenomenon that shook the very foundations of classical physics: the photoelectric effect. Why does light, which seems continuous, only knock electrons off metal surfaces at certain frequencies? And how did this mystery lead Albert Einstein to win the Nobel Prize? Get ready to see how a simple beam of light helped spark the quantum revolution. Fein Zone starts now. So, photoelectric effect occurs when a beam of light hits a metal plate, causing electrons to be ejected as if by magic. To explain this phenomenon, let's first understand the composition of metals. All metals have a specific crystalline structure that determines how their valence electrons behave. These electrons exist within an energy range known as the conduction band. Unlike in nonmetals, these electrons are not tightly bound to individual atoms. Instead, they move freely within the metal, forming what we call the electron sea. Now that we understand where these electrons come from, we can explain the photoelectric effect. When light strikes the metal, some of these free electrons in the electron sea absorb energy from the incoming photons. If the energy is high enough, the electrons are ejected from the metal's surface, creating the effect we observe. At this time, you may be questioning how something so simple got Nobel Prize. Well, if it seems simple, you're missing the bigger picture. A major question in physics is light a wave or a particle? Today, we know it's both, sometimes behaving like a particle, other times like a wave. But when Einstein explained the photoelectric effect, light was thought to be only a wave. By now, those who thought it was simple might be asking, how can light be two things at the same time? Maybe no one can fully answer that, but we can help you understand why light must be a particle to explain the photoelectric effect, yet also a wave, as Maxwell's equations describe, to explain all of electromagnetism. This duality became one of the pillars of quantum theory. So, to understand how electrons absorb light, we must take a step into the quantum world. Quantum mechanics tells us that light is made of discrete quanta, later called photons, each carrying energy proportional to its frequency, as described by the equation. Energy equals h times frequency, where h is Planck's constant. For an electron to escape, this energy must exceed the energy holding the electron in place, known as the metal work function. Thinking of light as photons explains why many red light photons, even though they sum more energy than a single ultraviolet photon, cannot eject electrons. However, a single ultraviolet photon can still eject one electron. However, something is still missing. With our current understanding, we might think that if the metal's work function is 4 electron volts, and we shine a single ultraviolet photon with a frequency around 2 petahertz that provides 8 electron volts, we lose 4 electron volts in the process. We know energy must be conserved, so we need to understand where the missing energy goes. At this point, it should be clear that even with twice the energy of the work function, we can't eject 2 electrons, because 1 electron will fully absorb the photon. Einstein thought about this and postulated that the energy absorbed from the photon, remaining after the electron's ejection, is converted into kinetic energy. Fein Zone for today has come to an end. I hope you enjoyed the video. Don't forget to leave a like, subscribe, and share your thoughts in the comments. Until next time, stay curious.